All right, so today we're starting 8.2, which is graphs of polar equations. And by the end of today, you are going to be able to sketch graphs of these polar equations. So I asked you to read the intro and then to read through example 1, and then you had some questions that you had to answer and some things that you had to graph. Okay, so your graph is going to consist of all the points P that have at least one polar representation. Remember, it's going to be r theta. We talked about that yesterday. And then they just gave you an introduction to the difference and the similarities between the graphs, which we already looked at in our treasure hunt packet. So you have the rectangular grid, which is going to use points that go up and down, left or right. With your polar grid, you're using the angle measures, and then your number r, which is the distance from the center to your point here. So this is what we are going to start graphing today. So we already talked about plotting points. Now we're going to be creating graphs with those points. So I asked you to look at example 1. And in example 1, they were sketching a graph of r equals 3. And what was that graph? Yeah, the questions are going to get harder as we go on today, guys. So the graph was what? Circle. Okay, a circle. So when r equals 3. And what did you notice about this circle? What's a characteristic about it? The radius is 3, right? If r equals 3, then the radius happened to be 3 here. And one thing I like is they tell you that the graph consists of all the points whose r coordinate is 3. So every single point on this graph has the radius of 3, which is how it creates that circle. So then I asked you to answer a few general questions, such as if you're given the polar equation of r equals n, where n is any integer value, what shape can you assume this will make? What shape? Circle. A circle. And then what would the radius be? N. Your n value, okay? Whatever your n value is. Okay, so it will create a circle. Whatever the n value is, that will be your radius. And then I just wrote a little note that says the graph is going to consist of all points that have that radius n, and that is how it creates your circle. Now, I asked you to graph that equation from example 1 on your graphing calculator. And to do this, you have to switch the mode on your calculator. So if you go to your mode, most of you are probably in function form, right? The mode button is right here next to your second button. So if you hit mode, okay, instead of function, I'm going to highlight POL. Okay, which is the polar coordinates. Okay, we'll actually use every mode this year. Fun fact for you. Alright, so now that I'm in polar coordinates, if I go to y equals, I no longer have y equals, I have what? R equals. So I'm going to do r equals 3, which was example 1. And then you can go ahead and graph it. Most of you are going to be in your standard window. And if you're in your standard window, this is what happens. Now, that doesn't look like a circle. That looks more like an oval to me, right? How do I know for certain that this is a circle? Yeah. Okay, so it has a radius of 3 everywhere, right? It's 3 up, 3 down, 3 to the left, 3 to the right. Now, if you want it to look more circular, if you go to zoom, and there's a z square, which is number 5. If you press that, then it looks a lot nicer. So it's just the dimensions on the calculator which is making it look distorted. So if you go to the z squared, then it's going to be more circular in shape. All right. Okay, so now what we're going to do for example 1 is we're going to sketch a graph of the polar equation. And we also have to express the equation in rectangular coordinates, which is exactly what we did yesterday. All right, so let's look at part A. So for part A, we have theta equals pi over 3. This is different from the last one because remember the last one we had r equals. Now we have theta equals. So what this does is this graph represents, I'm going to say consists. Sorry. This graph consists of all points whose theta coordinate is pi over 3. Right? And for this one, we're actually going to go ahead and graph it first. So if I do all points whose theta coordinate is pi over 3, I would be at all of these places and in between where I'm going to put these points. So all of these are at pi over 3. And if my r value was negative, it would continue. Right? If my r value was negative, all of those points would be pi over 3. Now, when I connect all those points, it's going to form what? Say it again. A straight line, right? And when you're doing your polar coordinates, if you guys want to use a marker or a pen so that it shows up better, that's perfectly fine. It is difficult to see pencil on those. So it is going to be a straight line. So it says describe this graph. It is a straight line on pi over 3 that goes through the origin. Okay, so it's going to continue, okay, back here because again, those are for your negative r values. Now the cool thing is when it relates to rectangular coordinates, you're going to notice some similarities between things you've already learned in Algebra 1 and Algebra 2. For instance, if it's a straight line, it's what type of function? Linear. And if it's a linear function, what is the most common kind of linear function? Y equals mx plus b, right? So when you're creating the rectangular, or really transforming the rectangular coordinates, you are going to have an equation that should be in the form y equals mx plus b. Now, if it goes through the origin, what's your b value? 0. Okay, so you are going to just have an equation that is y equals mx, where m represents your what? Or represents your slope. Okay, now it is a little different how we're going to get there, so I'm going to walk you through that. So to do the rectangular coordinates, you want to use the tangent of theta equals y over x. Now in this case, we know that theta is equal to what? Theta equals pi over 3. Okay, so what I'm going to do is I'm going to substitute that in. So if I have the tangent of pi over 3 equals y over x, what is the tangent at pi over 3? Root 3, right? That's something that we can calculate pretty simply, right? You guys remember the tangent? Root 3 over 3, 1 root 3. Okay, so root 3 is equal to y over x. Now remember I said what you want to have is y equals mx plus b. So in order to get that, what would I do to both sides? Multiply by x, right? So if I multiply both sides by x, I'll end up getting y by itself, x times root 3, and then we're just going to put it in the proper form, of root 3 times x. And then make sure if you do have a radical that your x is not inside that radical. Okay, so the tangent of pi over 3, we simplified that to root 3, and then we just solve for y. So those are going to be our rectangular coordinates. Now, if we wanted to have a general, bless you, formula for what this would be, we could actually create that. We could actually do that. This is y equals, so this is your form of your rectangular coordinates. It would be y equals the tangent of theta times x. Because for this one, the tangent of theta was the tangent of pi over 3, and that was root 3. Okay, you don't necessarily have to use that form, but I'm just telling you, if you have theta equals, it will be this form. Okay, it'll always be the tangent of theta multiplied by x. Right, because you'd always do the same steps, the same process. All right, so that's one type of polar equation. Now we're going to go to B, which is r equals negative cosine of theta. So for this one, we're actually going to find the rectangular coordinates first, and we're going to do that using some strategies that we used yesterday. So yesterday when we were trying to do rectangular coordinates, we started out with something similar. Do you guys remember what you would do first? Hunter, do you remember? Yeah, Anna, what is it? Multiply both sides by r, right? Okay, so if I multiply both sides by r, I'm going to have r squared equals negative r times the cosine of theta. Okay, and then Hendrik, what do I do after that? Okay, so get out your notes from yesterday. And we'll look at the back page. Okay, so on the back page, you have those two information boxes at the top. Okay, and they have some special equations in them. Okay, good. So we know r squared equals x squared plus y squared. And then, Colin, what about on the other side?
You substitute r times cosine for x.
Good. So then I just have negative x. Okay, Kaden, what do I do after that?
Take the x over to the other side.
So that I can do what?
Complete the square.
Good. So I have to get everything on one side so I can complete the square. So this is x squared plus x, and that's where I'm going to complete the square, plus y squared equals 0 plus blank. Okay, now to fill in that blank space, I do half of b. So my b value is what? 1. So half of 1 is 1/2. So I'm going to do 1/2 squared, which is going to be 1/4. And then remember, I like to leave it like that so that I can factor. So this would be x plus 1/2 squared plus y squared equals 1/4. Okay, so that's going to be your rectangular coordinate. Now remember that this equation is the equation for what? A circle. So that is going to be our shape on the polar graph and in the rectangular. Okay? Now, if this is a circle, do you guys remember how to pick out the center? Yep, so HK, which is negative 1/2, comma, 0, just 0, right? Okay, so this would be, the center would be negative 1/2, 0. And then what would the radius be? Nope. Other way, square root it. 1/2. Okay, and to find the radius, you just take the square root of 1/4, which is 1/2. Okay, and you're going to see that this is going to happen on our graph here. Okay, so like I said, that is a circle. We'll graph it, and then we will describe it. Okay, so what you can do if you want to generate a list of values without using your calculator at first is you can make a table and use values that you know from the unit circle. Just like we would make an XY table, we are going to make a theta R table. Now, it is theta and then R, even though the points are R theta. Right? So one value I could plug in is 0, because 0 is a special place on the unit circle. If I substituted that in, okay, if I plug in 0 here, negative cosine of 0, what's the cosine of 0? What's the cosine of 0? 1. So this would be negative 1. Okay, now the next point I would go to, I probably wouldn't do pi over 12. Why? I don't know what that is, right, off the top of my head, because it's not exact on the unit circle. So then maybe I would do pi over 6, pi over 4, pi over 3, we'll do pi over 2, and then I'm going to show you some other tricks. Okay, so for pi over 6, if you plug that in, this is the opposite of the cosine at pi over 6. What's the cosine at pi over 6? Root 3 over 2, so this is negative root 3 over 2. Okay, this would be negative root 2 over 2. This would be negative 1/2. At pi over 2, what is the cosine? 0. Okay, so I'm going to graph the first one, which is 0, negative 1. Remember, if it's negative, you have to go in the opposite direction from your theta. So if it's 0, I wouldn't put 1 here. I have to do the reflection, which would be right here. Now, when I go to graph something like negative root 3 over 2, I am going to want to visualize that as a decimal so I can put a good estimation on my graph. So this is going to be negative 0.87. And in just a little bit, I am going to show you how you can use your calculator to get these values. And then for negative root 2 over 2, that's going to be negative 0.71. Obviously, negative 1/2 is 0.5, and then you have 0. So just watch me for a minute, and then I will give you time to put those on. So for pi over 6, if it's negative, okay, remember you're going in the opposite direction. You always know what line it is because see how this is pi over 6? It's going to extend to something that's also over 6. Okay, so you do want to just do that carefully. So you have 0.87, so I'm going to estimate about right there. And then I have 0.71, which is going to be very close, and that would be at the pi over 4. And then pi over 3 is 1/2. And then at pi over 2, I have 0. Okay, so what I actually created right there is half of my circle. The other half of the circle is symmetric to the bottom half. Okay, so really, if I know that at pi over 6, I was at negative 0.87, here I know I'm going to be at 0.87, and then 0.71, and then 1/2. And so I can go ahead and make the other part of that circle. Now remember what I said before, how the radius is 1/2 and the center would be at negative 1/2, 0. If I plot negative 1/2, 0, I'm approximately right here. Okay, so you can see the radius is 1/2, okay, and the center is right there. Okay, now I used estimation because I knew that was going to be a circle. What we are going to end up doing is we are going to use our table on our calculator. So I'm going to just give you a note here. And we are going to do this for our next graphs. So you can set your table on your graph to go by pi over 12. Now, why would pi over 12 be significant? Why did I choose pi over 12? That's what it's going by, right? Isn't this 1 pi over 12? What is 2 pi over 12 reduced to? Pi over 6. 3 pi over 12. 4 pi over 12. 5 pi over 12. 6 pi over 12. Can you guys see the pattern there? So that's why I would choose pi over 12, because that will show you a point on every line. So you can set your table on your graph to go by pi over 12, which will give you a point for each line on the grid. Okay, now we are going to describe this graph. So this graph is a circle with the center -1/2, 0, and radius 1/2. Okay, and I am going to show you how to do this on your calculator so that when we do it on the next one, you guys can try it. All right, so I'm just going to go to my y equals, which is now r equals, and plug in the opposite. So I use my negative button of cosine. And then look, when I do x, it gives me my theta. And then if I go to my table set, I want my table to start at 0. And then I'm going to type in pi over 12. Okay, so my table start is 0. My change in my table is pi over 12. So now when I go to my table, I have 0, -1. That's something I already graphed. This would be at pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2. Okay, so you could plot a point on every single line. Now, for some of them, that's not going to be necessary. On others, you are going to want to put more points on there. Okay, so that's something that we're going to be building off of. And again, if you wanted to graph it, you could go ahead and do that. Now, when you graph it, look how tiny that is. Okay, what you can do is you can change your scale. You can zoom in. When you're graphing this, there you go. When you're graphing this too, this is pretty small. If you do have a lot of decimals, you can change your scale of your graph. So you could go by halves. You could go by, we're going to have to go by 2 sometimes because it'll be too large. So that's something to keep in mind too. Yeah, JC?
You say your y to.
Say it again.
What'd you set your y to?
My y?
Or when you did it?
Oh, the r?
Yeah.
So the original equation, the opposite of cosine of theta. Yeah. All right. Now, when we flip over to the next page, we're going to have some generalizations that we're going to talk about. Right? Now, these are just some generalizations about different equations that are going to produce different types of graphs. Okay, so there are graphs that are going to be of this form, which is the form r equals 2 times some number a multiplied by the sine of theta, and r equals 2 times a times the cosine of theta. And those are going to be circles if they have that form, where the radius is going to be the absolute value of whatever your A term is. Okay, so A is just an arbitrary number in this case. Now, the center of that circle would be at at A pi over 2, okay, and A0. And then we have another type of graph that is called the Lamasson. JC, did I do a good job?
Yeah, you did great.
Okay. So it is a French word for snail, which is going to,
I don't think that means, you sure that means snail?
it's a Latin root. I think the direct translation in French is cochlear.
That's gargoyle.
That, no. Is that what it is?
See what the thing in it.
So this is a special type of graph, which I'm going to show you what some of those look like in just a second. And it's going to have the equation of something added or subtracted on the outside. So a value plus or minus b times the sine of theta, or a value plus or minus b times the cosine of theta. And there is a special one that's called a cardioid. Okay, because a cardioid, the root word of that is similar to what?
Cardio.
Okay, yep, which has to do with
Your heart.
your heart. Okay, so this gets its name from the heart-shaped figure. Some people think it looks more like a badonkadonk than a heart, but it is an upside-down heart. Yes. Okay, so it's an upside-down heart, right? It has a nice little curve there. Sometimes you have one with a circle in it. Okay, and then sometimes you have a convex. These are all the types of limasomes. Okay, so an upside-down heart, or Mr. Toby used to tell him it was butt-shaped. I prefer the term badonkadonk, as you can see. Okay, and then we're going to continue going over that chart in just a few minutes. So if it is a cardioid, it has the same form, except A and B are equal to each other. Okay, so those two values would be the same. And you could also write the equation in these forms. The forms of the equations are not something that you're going to have to know, like at the top of your head, but it is helpful if you recognize the form, that you can figure out what the shape is going to look like. Okay, so I want you to understand that with these graphs, there is a general form of those equations, and you can use those to classify what type of graph you're going to have. Okay, so for our next example, and actually before we do our next example, I said to look in your text at page 549 so you can see the shape for relation. So I was just going to show you that real quick. So this would be if you had 2 sine of theta, your figure 4 here. You can see that you have a circular shape. Okay, and that was for the first type. And then we are going to practice your next 2 types. All right, so the first one is 1 plus the sine of theta. And again, we are going to relate this to something that you've already done, which your main benefit is to see how these are all connected. And then I'm going to show you how you can use your calculator to generate those points as well. So if we're graphing r equals 1 plus the sine of theta, we actually know how to graph this already in rectangular coordinates. So that's exactly what we're going to do. So if I'm going to sketch this in rectangular, I would just have y equals 1 plus the sine of theta. Do you guys remember that we did that in chapter 5? Yes, you remember it fondly? Okay, so if I have 1 plus the sine of theta, I'm just going to draw This is going to be a very casual graph. Okay, so what is my maximum value going to be on my y? What's the maximum value of sine? 1. So if I have the sine of theta plus 1, what's my maximum value? 2. Okay, so I'm going to go up to 2. I'll go down to negative 2. But what is my minimum value going to be? 0. Yeah, why is it going to be 0? So negative 1 plus 1 will be 0. Okay, so we're just going to use some quick and simple points. Pi over 2, pi, 3 pi over 2, 2 pi, which is one complete rotation, right? One period. All right, so for sine, if I were to start at 0, what's the sine of 0? 0. 0 plus 1 is 1, so I would be right here. Now, do you guys remember how we did it from there? So if I'm at 1 at 0, what's the next point that I know? Did I say it wrong? So if at 0 I'm at 1, what's the next point that I know? 2 pi, I'm at what? 1, because that's the end of the period. Then for sine, what happens halfway in between? It's the same. What happens halfway in between these 2 points? It goes to the maximum. Halfway in between these 2 points, it goes to the minimum. Okay? Hopefully we remember that from chapter 5, right? You start at 0, you go to the end of the period, halfway for sine you're in the same place, halfway you do the max, halfway you do the min.
For these ones, can you scale them so I can?
Yes. Yeah. Okay, so then what we're going to do is we're going to use these to create our table. Okay, so use points from graph on our table. Okay, so again, remember that your table is theta r, even though when you plot your points, it is written as r theta, okay? Because you can't do r until you know what your theta is. All right, so the points that I have here, at 0, I was at 1. At pi over 2, where was I? 2. At pi, 1. At 3 pi over 2, I was at 0. And at 2 pi, I was at 1. Okay, so what we're going to do is we're going to plot those points on our grid. Now, when we do that, we are going to label our points on our grid with letters. And this is something that you're going to have to do for your test too, which is why I want you to practice it now. So I have 5 points, A, B, C, D, E. And then once I plot them on my grid, I am going to label them. Now, when I am plotting these, I don't want you to connect them yet. Okay, so we're just going to plot these points. You guys should be able to plot all those without me. Think you can do it? Some of you already do it. Okay, so I'll give you a second to get a head start. So you're just plotting those points. Okay, let's see how we did. So at 0, I'm at 1. So 0, 1 is right here. And then at pi over 2, I'm at 2. So I'm going to go 1, 2. At pi, I'm at 1. And then here I'm at 0. Okay, and then I'm back here for E. So I have A, B, C, D. I should have waited for that one, but that's okay. E. Now, just so we have a clear picture of what I just graphed, it's really this. Boom, 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 boom. Which, is that going to look like an upside down heart if I just connected those points? Okay, no, you have to connect them in a certain way. So in order to make sure that I have the right curve, I'm going to just do some checking with my graphing calculator. Okay, so I'm going to go to y equals, I have 1 plus the sine of theta, not that, sine of theta. Okay, and then again, I'm just going to go to my table set. I want it to start at 0. I want to go by pi over 12, which I already have in there from last time, which you're going to start to notice that pi over 12 is that 0.26. So now when I go to my table, I am going to, just want to make sure I had that. Okay, I'm going to look at each line and see what points I want to plot. So 0, 1 I already have. The next one is 1.25, which I could put on there. But the one after that is 1.5. And so I think that's a good one to put. And then after that, I have 1.7, 1.86. Right? So I can see that what I'm doing is I'm creating this curve here. So I'm going to go ahead and put that on. Now the other side you're going to see is symmetric. Once you get to, you can see your pi over 2, because you should recognize that as 1.57. Do you guys see that on your calculator? So I'm just going to scroll up. That's what I usually do, is I try to get myself to points that I can see. And then I'll either write them down in a grid, not as the decimal, but as the line that I'm graphing. So I'm at 2, and then again, these are going to be symmetric, right? So if I'm here at 1, I'm at 1.25, 1.5. So I might put that on there, and then I'm just going to connect these so that they are symmetric to each other. Now, you can also use this to graph. Mine is zoomed in. So you can kind of see what happens here, how you do have that curve. Okay, so you have that rounder shape. And then if you go back to your table, you can see exactly where that curve is happening. So I was just at pi, which is where I knew I was at 1. So I'll just put that to the top. So see how I have pi here at the top? So then I'll just go to my next line, which is 0.74, and then I have 0.5 here. Okay, which is on 7 pi over 6. So then what I'm going to do is connect that, and then I'm going to have this be symmetric. Okay, and then this one's actually, I don't like that as much. Because if I'm 1, 2, 3, 4, 1, 2, 3, 4, I want to make sure I have that same curve here, and that one seems a little bit lower. Right, so you do want to make it as symmetric as possible, especially when we start to get into the rose curves. So again, you can use your calculator to figure out some of those blank spots. You will have points that you have to label for your test. I am going to give you some polar graph paper for the part of your homework that you are doing tonight. So here are some common polar curves. The first ones are the circles and the spiral, which we didn't look at a specific example of a spiral, but that is something that you could have. And then, like I said, the limasones, that is a Latin root and a French word for snail. Okay, and then you have these different types of curves. So you have these different types of limasones. Some are going to have a loop on the inside, and it doesn't have to be just upside down. Okay, these can be any way. So you could have one that has a loop on the side. They kind of look like kidney beans. Okay, you could have one that's rotated here. Okay, so that could be rotated in any direction. And then we're going to start talking about the rose curves. So you have a 4-leaved rose, which is going to be common, a 5-leaved rose, 3-leaf, 8-leaf, and then you also have lemniscates, which are going to be figure 8s. Something also interesting about the limasones is they were rediscovered by Blaise Pascal's father, who is, or what is Blaise Pascal famous for? Pascal's triangle, which you guys used last year in binomial expansion. Okay, so I am going to start the next one with you. Alright, so we're sketching a graph for this rose curve.